Hello, students. So the goal of this particular lecture is to introduce a new topic that isn't directly related with sequences at all. We've gotten really good at studying sequences. I want to introduce two new things that you'll remember from Calc 1 even as being important. The idea of what the limit of a function is and what continuity means. And so let's even just start by trying to motivate the correct epsilon delta definition of the limit of a function. So, right, let's go off to the side and maybe motivate it a little bit. So when one says the limit as x approaches p of f of x is equal to L, on the one hand that should mean something like as x gets close to p, f of x gets close to L. Right, of course that's what it means. And let's just try to get a little bit more precise. So let's maybe get a little bit more precise by doing this. What does x getting close to p mean? Well, that should mean that absolute value of x minus p gets small. What does f of x getting close to L mean? That means absolute f of x minus L gets small. So let's go from there. When one says the limit as x approaches p of f of x is equal to L, that's intuitively what it means. Let's get a little bit more precise. So maybe we'll say it this way. No matter how small you want f of x minus L to be, you can arrange by taking an absolute value of x minus p small enough. And now you definitely know what I'm going to go for. No matter how small you want absolute value of f of x to be, that means that there's like a universally quantified thing. For every epsilon bigger than 0, you can get absolute value of f of x minus L to be less than that epsilon, as long as absolute value of x minus p is small enough. So what does that mean? That means that there should exist some delta bigger than 0, such that if absolute value of, well, I'm going to give myself some space because there's going to be a technicality that I'll need to add some space right here. If absolute value of x minus p is less than delta, then absolute value of f of x minus L is less than epsilon. And something that you'll remember from Calc 1 is the limit of a function shouldn't actually care what the function evaluates to at p. And notice, this does, because if x is equal to p, then definitely absolute value of x minus p is less than delta, no matter what delta you put there. So that means absolute value of f of x minus f of p, x is p right now, minus L should be less than epsilon. For every epsilon, so that means f of p should just be equal to L. So in order to allow for this idea that the limit shouldn't care about what the actual value at p is, I'll do that. So that automatically, in the hypothesis of this if-then, excludes the case x is equal to p. And so now I don't care about what happens when x is equal to p. There's the definition. I'm going to take exactly this and copy it in the space provided in the notes. Let U be a subset of R. So U is going to be the domain of the function. Let f be a function defined on U. Let p and L be real numbers. Then I'll say that the limit as x approaches p of f of x is equal to L means for every epsilon bigger than 0, there exists a delta bigger than 0 such that, let's quantify what x is. So if you remember, over there I was plugging x into the function, so x better be in the domain, such that for all x in U, if the absolute value of x, this is a mistake that I'll make with some frequency. If 0 is less than absolute x minus p is less than delta, then absolute f of x minus L is less than epsilon. So if you want to show something's continuous, you need to prove exactly this sort of statement. And let's just demo that. Let's prove that the limit as x approaches 3 of 4x minus 2 is equal to. So you should already have a pretty good idea what I'm going to put here, but let's just try thinking about it. So let's be intuitive. That means x, I'm interested in what happens when x is close to 3. Well, when x is close to 3, 4x should be close to like 12, I guess. And if you take something close to 12 and subtract 2, you should get something that's close to 10. That should mean that this limit is equal to 10. Well, let's actually go through the proof. So this is exactly a Calc 1 proof that I'm about to do. It's a Calc 1 proof that you'll remember from Calc 1, and you'll probably remember finding difficult in Calc 1. And what I hope to convince you here is that you've matured quite a bit in your mathematical knowledge. Now this proof should be reasonably straightforward. So I want to prove a statement that looks an awful lot like this. And, well, that means I need to start by considering any epsilon bigger than 0. So let's do that. Let's consider any epsilon bigger than 0. Then I need to come up with a choice of delta. I have a formula for everything in sight, so I can probably get a formula for delta. So let's let delta be equal to, and you know the game, I'm going to put a blank there, we'll figure out what I really need delta to be. It'll be something that'll involve epsilon. Next, I need to consider any x in U. What is U? U is the domain of the function. What's the domain of this function? Well, it looks like it's all of the real numbers. So let's let x be a real number. And now I need to prove if this, then that, where what is p? It looks like p is 3. So let's assume this. Assume the hypothesis of the if-then. So let's assume 0 is less than the absolute value of x minus p. So that's x minus 3 is less than delta. I want to show that the absolute value of f of x minus L is less than epsilon. What is f of x? Well, I'm interested in this function. What is L? Well, there's the alleged limit. So I need to show that this minus 10 is less than epsilon. So let's try to do that. Yeah, there should be enough space, I hope. So let's just do that. Well, absolute value of 3x, nope, 4x minus 2, so there's f of x, minus 10. Let's just try to walk with that. Minus 2 minus 10 is the same thing as minus 12. That's absolute 4x minus 12. And I want to get this to be small, and I know that this quantity is small. So if I can make this into something that involves absolute x minus 3, that will make me happy. And, well, you see how to do that. It looks like I need to factor out a 4. Equals 4 times absolute x minus 3. So that means this thing is less than 4 times delta, because absolute value of x minus 3 is less than delta. I want that to be epsilon. Do you think I could take that off to the side and figure out what delta results in 4 times delta equal to epsilon? Yeah, of course you can. Now I know what choice of delta to use. So let's use delta equal to epsilon over 4. But that means 4 times delta is equal to 4 times epsilon over 4, which is exactly epsilon. And now let's just put a concluding sentence. Thus, for all epsilon bigger than 0, I started with considering any epsilon bigger than 0. So I did prove something is true for every epsilon bigger than 0. I came up with a choice of delta. So for every epsilon bigger than 0, there exists a delta bigger than 0 such that I then let x be an error. So I proved that something was true for every x in R. And what did I prove? Well, I proved that if this assumption was true, then this conclusion is true, that this thing is less than epsilon. If 0 is less than the absolute value of x minus 3 is less than delta, then absolute value of 4x minus 2, parentheses for emphasis, minus 10 is less than epsilon. So the limit as x approaches 3 of 4x minus 2 equals 10. Very good. So there's a constraint on when it makes sense to talk about limits, and let's motivate it really quickly. So in the definition of the limit, there's an if-then. And one thing that you know about if-then statements is whenever you're under the circumstance that the hypothesis of an if-then statement is false, then the whole statement is true no matter what. So imagine you had a function, f, and you tried to take its limit at some value p, but let's suppose that for every x in the domain of the function, this is false. For everything in the domain, x is far away from p. Well then, this if-then would automatically be true, so the limit of that function would be equal to L, but notice that would be true for everything. So let's just write that in words. Again, this will be informal. So if P is not close to anything in U, which just remember is going to be the domain of the function, then the limit as x approaches p of f of x equals L is true, and maybe for emphasis, no matter what L you use. And that's really bad. That would mean that you can write down a function, you can conclude that its limit is 5 and 7 and 23 and any other number you want. So that's just going to be a garbage thing to say. So I'll want to find a statement which will exclude those. So if p isn't close to anything in U, then I won't even try to take the limit at that point. The limit will be everything, and so just kind of won't be well defined. For a subset U and a point P, I will call P an accumulation point or limit point of U if for every delta bigger than 0, there exists an element of U such that 0 is less than the absolute value of x minus p is less than delta. So a point is a limit point or accumulation point if, no matter what delta you pick, there exists something where the hypothesis of this if-then is true. So the if-then is a reasonable thing to even ask about. A point P, which is not a limit point, is called an isolated point. And let's just try to let's just practice our negations and figure out what that means. So P is isolated means P is not a limit point. So it means not this. So it means not for every delta bigger than 0, there exists an x in U such that, and I know previously it was written as 0 is less than the absolute value of x minus p is less than delta, but in order to make it easier to negate, I'll write that down as two inequalities. All right, so let's negate that. So when you negate that, when you negate a universally quantified thing, you get an existentially thing, so that must mean there exists a delta bigger than 0, such that for all x in U, the negation of this and is true. When you negate an and, you're going to get an or. When you negate this inequality, you'll wind up with, let's see, that'll be 0 is greater than or equal to the absolute value of x minus p. And, well, this is going to be scratch work, so maybe I'll underline it in red. 0 is greater than or equal to absolute value of x minus p. Or absolute value of x minus p is bigger or equal to delta. And I want to focus on this one in red because that obviously should be simplified. So absolute value can never be negative. So this thing in red is the same thing as 0 is equal to absolute x minus p. But there's only one thing that has absolute value 0, that's 0. So that really just means x minus p is equal to 0. So x is equal to p. So what does this mean? This means that there exists a delta such that for every x in U, either x is exactly equal to p or x is far away from p. So let's write that definition down. I'll call a point P in U isolated if, and even though I just got one, I'll write this two different ways. There exists a delta bigger than 0 such that for all x in U, either x is equal to p or absolute value of x minus p is bigger or equal to delta. And that's just, I'm going to reformulate that just a little bit more. So an equivalent definition, there exists a delta bigger than 0, great. And let's unravel the rest of this. So this says, for every x in U, either x is exactly p, or absolute value of x minus p is bigger than or equal to delta. So that means if x is not equal to p, then this must be true. So you could rewrite this as saying for every x in U, except for p maybe, absolute value of x minus p is greater or equal to delta. Nice. So the next thing that I want to say is what it means for a function to be continuous. And you'll remember this too. Let's let U be a subset of R, let f from U to R be a function, let P be an element of U. And here I want to emphasize something. In the definition of continuity, I will need that point P to be an element of U. Up here, there's no such constraint. Right here, it's just P is an element of R. Except really, I also need up here I also need P is a limit point of the domain U. So limits make sense at limit points. You can only ask about continuity at points in the domain. So carrying on, we say that f is continuous at p if, and something super similar, right? I need, as x gets close to p, f of x should get close to f of p. So I say that f is continuous at p if, for all epsilon bigger than 0, there exists a delta bigger than 0, such that for all x in the domain u, if absolute value of x minus p is less than delta, then absolute value of f of x minus f of p is less than epsilon. And another difference that you'll notice is right here there's no 0 is less than nonsense, which does appear in the definition of the limit. And now you could add it in there and you would get the same definition, because the only thing that would exclude is the case that x is equal to p. But that if then is already true when x is equal to p, because f of p minus f of p is equal to 0, which will be less than epsilon. I will just say a function is continuous on u if for all p in u, f is continuous at p. Or said another way, I know what it means to be continuous. Let's just expand everything out. For all p in u, and for all epsilon bigger than 0. So I'm just going to copy down the definition of continuity. There exists a delta bigger than 0 such that for all x in u, if absolute x minus p is less than delta, then absolute f of x minus f of p is less than epsilon. Cool. So, let's use this definition and let's just check something. So here's a function, f of x is equal to 3x minus 2. I claim this is continuous when x is equal to 1. So let's just go ahead and check that. So that means I need to prove something is true for every p in the domain. Again, this function is defined everywhere, so its domain is R. So let's consider any p in the domain R. And let's consider any epsilon bigger than 0. I have a formula for this function, so chances are I can get a formula for the choice of delta that I need, but I don't know what that formula will be until I've figured out what that formula needs to be. Excuse me. So I'll let delta be something that I get to choose. Next, I need to prove something is true for all x in u. So let's let x be an element of, the domain in this case is the real line. And the thing I need to prove is that if this, then that. So let's assume the hypothesis of that if then. Let's assume absolute value of x minus p is less than delta. Then I need to show that the absolute value of f of x minus f of p is less than epsilon. So let's just go through the walk of trying to show it. Let's just expand out absolute value f of x minus f of p. That is equal to absolute value of f of x is 3x minus 2, parentheses for emphasis, minus f of p, parentheses because they're important, 3p minus 2, there's f of p. And now let's just expand that around. That'll be the same thing as, well, we can even do, well, yeah, let's do something, multiple steps all at the same time. You'll see that this minus 2 will cancel with this minus 2, which will leave me with absolute 3x minus 3p. And the one thing that I know is that x minus p is small. absolute value of x minus p is small. So how can I turn this into something that looks like it has an x minus p? Well, how about if I factor out a 3? Oops, not equals. Is less than 3 delta. I know that the absolute value of x minus p is less than delta. I certainly do not know that the absolute value of x minus p is equal to delta. All right, and now, well, the same game. Is there a choice of delta that you could make, which would result in 3 delta being equal to epsilon? Of course there is. Let's let delta be, I guess, epsilon over 3. Then you would wind up with 3 delta is the same as, and you know what? In order to make this more readable, is less than 3 delta equals 3 epsilon over 3 is just epsilon. Oh, neat. So let's read that. So what have we done? We considered any p in R. So thus, for all p in R, and for all epsilon bigger than 0, there exists a choice of delta bigger than 0. Let's actually just meditate on that for a second. Is this positive? Yeah, it's a positive divided by 3. It's positive. Such that for all x in R, because we assumed x was in R, if the absolute value of x minus p is less than delta, then absolute value of f of x minus f of p is less than epsilon. So this function f is continuous on all of the real line. Cool. So let's so there's another definition of continuity that maybe you'll remember as being like the definition from Calc 1. You say that a function is continuous at a point p if the limit of that function at that point is the same thing as plugging p into the function. Let's see to what degree that's actually true. So, summarizing stuff on the previous page, if I give you a function defined on u, I can ask about limits of that function as long as you look at limit points. Of the domain. Given a function defined in a domain, you can ask whether or not a function is continuous at points in the domain. And one thing that maybe I'll point out, not every point in a set is a limit point. Let's draw an example. So let's suppose your set U consists of, well, here I'll color code to make this walk. So there's the number line. The set U I will draw in red. So maybe the set U consists of that half open, half closed interval together with that point right there. Well, then you see a few things. This point, say right here, this point is in U, and this point is a limit point of U. Limit point of U. This point right here is not in U, but P is a limit point of U. This isolated point over here is in U, but it is not a limit point. Neat. So what does that mean? That means that at, let's do more color coding. At this point, continuity makes sense. You can ask about continuity. But you can't ask about the limits. Or if you do try to ask about the limit, you'll get that the limit is absolutely everything. At this point, which is not in U but is a limit point, you can ask about limits but not continuity. Limits make sense. Continuity does not. So I won't say that a function is or is not continuous at that point. At this point right here, you can ask about limits and you can ask about continuity. And this brings us to the theorem that I want to hit today. Let U be a subset of R. Let F be a function defined on U. Let P be in U. And let P be a limit point of U, or accumulation point if you like that language better. I'll switch mostly to limit points as being the word that I'll use. Then, the conclusion of this theorem is that a function is continuous at P if and only if the limit as x approaches P of f of x is equal to f of P. So what this means is this could be taken as your definition of continuity as long as you are willing to only look at limit points. So let's do that. And the proof is actually pretty straightforward. The proof will be straightforward because the definition of limit and the definition of continuity looks so very similar. So let's suppose that f is continuous at P. And maybe just for help, I'll put the want to show. So I want to show the limit as x approaches P of f of x is equal to f of P. And as long as this is just very scratch walk looking anyway, what does that mean I need to show? I need to show that for every epsilon bigger than 0, there exists a delta bigger than 0, such that for all x in the domain U, if 0 is less than the absolute value of x minus P is less than delta, then absolute value of f of x minus f of P is less than epsilon. That's what I need to show. And all that should be regarded as scratch walk, not part of the actual write-up, but that tells me how the actual write-up should go. I need to start by considering any epsilon bigger than 0, because I need to prove something is true for every epsilon. I now need to come up with a choice of delta. I don't have any formulas for any of these functions, for the function f of x, so there's no hope of me having an explicit choice of delta. But what do I know? I know that this function is continuous at P. So I can use the fact that this function is continuous in order to conclude, well, I've already declared epsilon, so I don't need to declare epsilon again. But I see that the definition of continuity holds. The definition of continuity, let's scroll up, says some stuff, for every epsilon bigger than 0, some stuff follows. I've picked an epsilon bigger than 0, so I can just jump to the stuff that follows. So because f is continuous at P, by assumption, I see that there exists a choice of delta bigger than 0, such that for all x in U, if the absolute value of x minus P, and in fact, I think I maybe even want to offset this a little bit. I'm going to put the if-then on kind of its own line. If the absolute value of x minus P is less than delta, then the absolute value of f of x minus f of P is less than epsilon. All right, so that gives me a choice of delta. No guarantees that it'll be the choice that I need, but I think it probably should be. In the statement of the thing that I want to show, right? I want to show this. So I want to show that for every epsilon bigger than 0, I started by considering any epsilon bigger than 0, great. There exists a delta bigger than 0. Yup, I've found a trace of delta. I need to now prove that for every x in u, so I should consider any x in u. If this is true, then that is true. How do you prove an if then? Assume the hypothesis, prove the conclusion. So I'm going to assume about this x that 0 is less than the absolute value of x minus p is less than delta. Ah, wait, but in particular then, I have the absolute value of x minus p is less than delta. Right, because 0 is less than the absolute value of x minus p is less than delta is just 0 is less than the absolute value of x minus p and the absolute value of x minus p is less than delta. But what do I know? I know that if absolute value of x minus p is less than delta, then absolute value of f of x minus f of p is less than epsilon. So I can use the continuity of f to now conclude that absolute value of f of x minus f of p is less than epsilon. And so we're done, I think. So let's just write the concluding sentence. Thus, we have shown that for every epsilon bigger than 0, because we started by considering any epsilon bigger than 0, there exists a trace of big delta. There exists a trace of delta. Sorry, I said big delta. That's just delta. So that for every x in the domain u, we consider any x in u right there. If 0 is less than the absolute value of x minus p is less than delta, we assume that 0 is less than the absolute value of x minus p is less than delta, then f of x minus f of p is less than epsilon. We concluded that absolute value of f of x minus f of p is less than epsilon. And when I speak in WODs just out loud, you'll notice that a lot of times I'll accidentally leave out the absolute values. I'll do my best to actually write them. Nice. So let's prove the reverse implication. Let's prove that if the limit as x approaches p of f of x is equal to f of p, then the function is continuous. So let's assume that the limit is x approaches p of f of x is equal to f of p. And let's put down the thing that we want to show. I want to show f is continuous at p. And what does that mean? That means for every epsilon bigger than 0, there exists a delta bigger than 0, such that if absolute value of x minus p is less than delta, then absolute value of f of x minus f of p is less than epsilon. So I want to prove something is true for every epsilon bigger than 0, so I should start by considering any epsilon bigger than 0. The only way I have to get a hold of a choice of delta is using the assumption that the function has a limiting value, that the limit as x approaches p of f of x is equal to f of p. This is the only thing I know about the function. So let's expand that out. So because I know that, and I know that I have a positive choice of epsilon, I get to conclude that there exists a delta bigger than 0, such that for all x in the domain u, if 0 is less than the absolute value of x minus p is less than delta, then absolute value of f of x minus f of p is less than epsilon. This gives me a choice of delta. There's a choice of delta. That was a little bit ambitious right there. I should quantify x. So I need to prove something is true for every x in the domain u. So let's declare that. Let's consider any x in the domain u, and let's put the assumption. We now want to assume that absolute value of x minus p is less than delta. So let's consider any x in the domain u, which satisfies that assumption. All right, so this is going to take just a touch more work than the reverse implication. So if we knew that 0 were less than the absolute value of x minus p, then we would know that 0 is less than the absolute value of x minus p, and the absolute value of x minus p is less than delta. So we would have the if part of the if-then, which would give us the conclusion. So if 0 or less than the absolute value of x minus p that would make us happy, well, let's just make that one of the cases. So either 0 is less than the absolute value of x minus p is less than delta, or, well, the only thing that I assumed is 0 is less than the absolute value of x minus p. The only exception to that is the case that 0 is equal to the absolute value of x minus p. In the first case, we see that as 0 is less than the absolute value of x minus p is less than delta, our choice of delta implies absolute value of f of x minus f of p is less than epsilon, which is exactly what we need. So we're done in case 1. Let's think about what happens in case 2. In the second case, as 0 is equal to the absolute value of x minus p, we have x is equal to p. And let's think about what the conclusion we want is. We want this conclusion. Well, but if x is equal to p, then f of x is equal to f of p. So, absolute value of f of x minus f of p is equal to absolute value of f of p minus f of p, because x is equal to p. Well, but that's exactly 0, which is less than epsilon because epsilon is bigger than 0. So, let's just summarize that. In either case, we reach the conclusion that the absolute value of f of x minus f of p is less than epsilon. So, let's summarize. We started by considering any epsilon bigger than 0. So we proved something is true for every epsilon bigger than 0. We proved that for every epsilon bigger than 0, there exists a delta bigger than 0, such that for all x's in the domain U, if the absolute value of x minus p is less than delta, then absolute value of f of x minus f of p is less than epsilon. Thus, f is continuous. Neat. So, at limit points, continuity is exactly detected by limits. Let's think about what happens at non-limit points, that is, at isolated points. So let's let U be a subset of R, and f be a function defined on U. Let's suppose that P is isolated. I claim that f is continuous at P no matter what. And this kind of makes sense. So what does continuity say? Continuity says when you take an input that's close to P, you should get an output that's close to f of P. Well, but the only input close to an isolated point is that input itself. So that means the only x that we need to check is x equals p, and yeah, f of p is close to f of p. That's all. So let's do this. So let's consider any epsilon bigger than 0. The only assumption we have right now is that p is isolated. Let's remind ourselves the formal definition of isolatedness. There. P is isolated means that there exists a delta bigger than 0, so that for every x in U, either x is equal to p or the absolute value of x minus p is less than delta. Notice, there's a choice of delta. Maybe that's the choice of delta we need? I don't know. Since p is isolated, we have that there exists a choice of delta bigger than 0, such that for all x in U, either absolute value of, I literally just had it above, either x is equal to p, or absolute value of x minus p is bigger than or equal to delta. So now let's consider any x in the domain U, and let's assume that the absolute value of x minus p is less than delta. Oh, wait, but if the absolute value of x minus p is less than delta, then this branch of the OR statement is false. So it must be that this branch of the OR statement is true. So it must be that x is equal to p. But then we have something that's going to seem super similar. This means that the absolute value of f of x minus f of p is equal to the absolute value of f of p minus f of p, which is equal to 0, which is in fact less than epsilon. So what have we done? We have shown that for every epsilon bigger than 0, there exists a trace of delta, which actually, let's notice, in the way we declared our delta, we didn't make any reference to epsilon. Epsilon could be 1, epsilon could be a half, epsilon could be 1 over a billion. We could use the same delta. That's something worth noticing. So that for every x in U, if the absolute value of x minus p is less than delta, then the absolute value of f of x minus f of p is less than epsilon. So this video has gone on a little bit longer than some of the other ones, but sometimes that's just how things are. I'll stop here.